Welcome, curious minds and sleepy thinkers. You've found a soft place to land, a quiet harbor for thoughts that wander just before sleep. Tonight we will drift through one of the most magnificent and mysterious questions ever asked. What is nothing? Could it be a simple void, a complete absence of everything? Or does it hold a profound secret, a hidden potential that gave birth to the universe itself? Don't worry, we'll take it slow. This isn't a race through difficult equations or a lecture of hard facts. It's more like a gentle journey where we will float through a galaxy of ideas wrapped in a blanket of wonder and imagination. Let's not seek firm answers, but simply appreciate the beauty of the questions themselves, allowing our minds to wander wherever they may go. We begin our quiet journey by simply asking, what is nothing? At first, the answer seems so simple, so obvious. Nothing is nothing. It is the absence of everything. It is a room with no furniture, a page with no words, a vast, silent emptiness. It seems to be a void, a place of stillness, and a complete lack of being. But as we begin to look a little closer, and perhaps a little deeper into the cosmic story, we find that this simple picture of nothingness begins to shimmer and shift, revealing a far more profound and intricate truth. Let's start by imagining the grand stage of the cosmos. Picture the immense, incomprehensible vastness of space. Our mind fills it with shining galaxies, with swirling nebulae of stardust, with bright stars burning like lonely candles, and with the silent, devouring darkness of black holes. But what lies between these magnificent cosmic structures? What is in the great empty spaces that separate them? We might be tempted to call this nothing, but even here the story becomes more complex. In the deepest, quietest corners of the universe, far from any star or galaxy, lies a profound emptiness, a place where there's almost nothing at all. No sound, no light, just an endless cold quiet. But even in this desolate quiet, scientists tell us something is stirring. It's a concept that challenges our very intuition. The vacuum of space, this thing we would call nothing, is not truly empty. Instead, it is a restless, seething, bubbling ocean of potential. It is a kind of quantum foam, a froth of virtual particles that flicker in and out of existence in the blink of an eye. They are like tiny ghostly sparks appearing in pairs, a particle and its antiparticle, only to meet and vanish in a flash. This idea comes from the strange and beautiful world of quantum mechanics, a place where the rules of our everyday reality no longer apply. In this realm, the laws of physics suggest that even the emptiest parts of space are filled with a ceaseless humming activity. This isn't a violent, loud activity, but more of a quiet, energetic buzz, like the gentle hum of a distant electrical current, an endless murmur in the fabric of the cosmos. These virtual particles, though they exist for a fleeting moment, can have genuine, measurable physical effects, a whisper that leaves a lasting ripple. Now let us float with this idea for a moment. This nothing is not a blank canvas. It is a canvas that is already alive, a dynamic field of endless potential, full of a latent energy, waiting for the right spark. It's not a void, but a foundation. It's the stage upon which the entire cosmic play is painted, full of restless energy that is just barely contained. This changes everything about how we understand the word nothing. It transforms it from a simple lack into a foundational active component of cosmology itself. This whispering, humming nature of nothingness leads us to one of the most astonishing ideas in all of science, the theory of cosmic inflation. Imagine if this constant underlying energy of the vacuum, this restless hum of potential, were to fluctuate just for a tiny fraction of a moment. What if one of these quantum fluctuations, one of these ghostly sparks, didn't vanish immediately? What if it instead found a way to grow, to expand, to swell into something immense? The theory of cosmic inflation posits that our entire universe could have burgeoned from just such a vacuum fluctuation, a kind of nothing bursting into everything. This isn't just a leap of fancy. This theory, though still a subject of active research and debate, helps to solve some of the deepest puzzles about our universe. For example, it helps to explain why the universe we see today is so remarkably uniform. Everywhere we look, the cosmos appears to have the same basic temperature and density. Without inflation, we would expect a much more chaotic, lumpy universe, as different regions would have had no way to communicate with one another and even out their properties. But inflation suggests that the vast uniform universe we see today started from a tiny causally connected speck, which was then stretched to an enormous size in a fraction of a second. This stretching smoothed out any initial lumps and wrinkles, leaving us with the vast, consistent cosmos we observe today. This is a profound thought, isn't it? To think that the universe didn't just appear in a burst from nothing, but that it was already nestled within a state of nothing that was far from empty. A state filled with potential, with the possibility of everything. It's like finding a single seed in what you thought was barren soil, and then realizing that the soil itself is full of the very nutrients and energy needed to bring the seed to life. This cosmic soil, this quantum vacuum, is the true mystery. It challenges us to think beyond the simple traditional notions of emptiness or void, and into a realm where nothing is a dynamic foundational component of the cosmos itself. And this leads us to the heart of the matter. According to the principles of modern physics, the notion of nothing as a complete void or an absolute emptiness is a concept that's more philosophical than scientific. In the deepest, most fundamental sense, there is no such thing as an absolute nothing. There is always something. The quantum vacuum is the closest thing we have to a void, but as we've seen, it is teeming with life. It is the restless, vibrant, humming heart of reality. We can pause here and simply breathe with this idea. The world we see, the stars we admire, the galaxies that stretch across the night sky, all of them may have their roots not in a sudden violent eruption, but in a quiet, subtle, and profound restlessness that lay dormant within nothingness itself. The universe, in a way, is a product of this profound potential, a magnificent manifestation of a state that was never truly empty. The principles of quantum mechanics. A cornerstone of our understanding of the universe, at its smallest scales, paint a picture of a reality that is far more vibrant and alive than we could ever imagine. It tells us that the vacuum of space is not a peaceful, quiet place. It is, in fact, a field of endless potential, a sea of virtual particles that flash into and out of existence. These tiny ghostly sparks, these particle-antiparticle pairs, appear and vanish too quickly for us to observe them directly. But their existence leaves a measurable mark on the world. Physicists can measure their tangible effects, proving that what we call nothing is anything but empty. This is a beautiful and humbling thought. It suggests that even in its most desolate voids, our universe is a vibrant place. It hints at a deep and complex undercurrent to our reality, a ceaseless activity that lies beneath the surface of what we can perceive. It's like standing on the shore of a vast ocean. From where we stand, it may look calm and still, but we know that beneath the surface, there is a whole world teeming with life, a world of currents, creatures, and motion. The quantum vacuum is like that ocean. It looks empty, but it is in fact alive. Furthermore, this idea of a vibrant, restless vacuum is deeply tied to one of the most fundamental principles of quantum physics, the Heisenberg uncertainty principle. This principle tells us that there is a fundamental limit to the precision with which we can know certain pairs of physical properties at the same time. For example, we cannot know a particle's exact position and its exact momentum simultaneously. It is impossible. This principle suggests that even in what we might think of as a perfect vacuum, there are intrinsic uncertainties that prevent it from being truly nothing. The energy of the vacuum itself is subject to these uncertainties, which is what allows these tiny fleeting virtual particles to appear in the first place. This uncertainty is not a flaw in our measurements. It is a fundamental feature of reality itself. It is a kind of built-in fuzziness at the heart of existence, a gentle tremor that keeps the universe from ever settling into a state of absolute quiet. In this light, physics paints a picture of a universe where nothing in its purest form is an abstract, perhaps even an unreachable concept. The closest we can come to it is a state of perpetual restless potential, a state full of energy, of uncertainty, of possibility. It hints at the rich and complex underpinnings of our reality, suggesting that the universe we see in all its majestic complexity is but one possible outcome of an infinite number of possibilities that lay dormant within the heart of nothingness itself. And perhaps that is the most beautiful thought of all, that the universe is not just something that was created, but that it is the expression of a deep and fundamental potential that was always there waiting to be unleashed. And so we find ourselves standing at the edge of a new idea. Nothing is not a void, not a blank slate, but a dynamic foundational component of the cosmos. It is a bubbling, seething froth of virtual particles, a field of endless potential, an active and vibrant canvas upon which existence itself is painted. And it is from this canvas, this restless quiet, that the greatest story of all began, the story of the universe. Let us drift now deeper into the quiet heart of this new idea. We have come to understand that nothing is not a silent, empty room, but a restless sea. Now let's explore the very currents and tides of that sea, the hidden rules that make it so vibrant. This takes us into the beautiful and strange landscape of quantum mechanics, a kind of physics that whispers the secrets of nature at its smallest, most fundamental scale. Imagine a perfect, silent, and empty stage. In our everyday world, such a stage would remain forever still, devoid of all action. But in the world of the very small governed by quantum mechanics, this stage is a paradox. It is never truly silent. It is in fact alive with a quiet, constant hum. This hum is a ceaseless dance of tiny ghostly sparks, which we call virtual particles. They are like fleeting shadows or whispers in the dark, appearing for a single, unrepeatable moment before vanishing back into the stillness. These particles are born in pairs, a particle and its antiparticle. They flicker into existence from what we might call the quantum vacuum, a place that seems to our casual observation to be utterly empty. But this vacuum is not empty. It's a field of pure potential, and for a brief, glorious instant, it lends these ghostly pairs the energy to exist. A single virtual particle of light, a virtual photon, might suddenly appear only to meet its antiparticle and vanish, repaying its energy debt to the universe. This all happens so fast, in a blink of an eye, far quicker than we can even comprehend, that the rules of conservation of energy are never truly broken. It is a cosmic game of borrowing and returning, a ceaseless exchange that keeps the vacuum in a state of perpetual shimmering activity. You might wonder how we can be so sure about these ghostly sparks. After all, if they are so fleeting, how can we possibly see them or measure them? We can't, not directly. We can't take a photograph of them or catch them in a jar, but we can see the lasting ripples they leave behind. One of the most beautiful pieces of evidence for this unseen activity is an effect called the Casimir effect. Imagine two very thin, perfectly smooth metal plates placed incredibly close together in a perfect vacuum. You would expect nothing to happen. There are no air molecules to push them apart, no forces to pull them together. But they are, in fact, pulled closer. This happens because the vacuum between the plates, tiny as it is, restricts the types of virtual particles that can flicker into existence there. Outside the plates, in the vast open vacuum, all kinds of virtual particles can appear and disappear. They create a kind of constant, gentle pressure, a cosmic ocean pushing from all sides. But in the tiny gap between the plates, only virtual particles with certain wavelengths can fit, like waves that can only ripple in a very shallow pond. This means there are fewer of these virtual sparks in the gap than there are outside. This imbalance creates a tiny, gentle pressure pushing the plates together. It's a beautiful, elegant, and very real proof that even what we call a void is in fact a vibrant humming field of energy. The plates are not being pulled together by some mysterious force. They are being pushed by the silent roar of the quantum vacuum, a testament to the reality of these ghostly particles. This constant shimmering activity of the vacuum is a direct consequence of a fundamental law of quantum mechanics, a law so beautiful and strange that it challenges our everyday understanding of certainty. It is the Heisenberg uncertainty principle. In our world, we believe we can know everything about an object if we have the right tools. We can know its exact location and its exact speed at the same moment. But in the quantum world, this is impossible. The uncertainty principle tells us that there is a fundamental built-in blur to reality. We can never know certain pairs of properties with perfect precision at the same time. The more accurately you know a particle's position, the less you can know about its momentum, and vice versa. It's like trying to photograph a firefly in the dark. If you use a fast shutter speed to get a perfect picture of its location, you can't see the motion, so you don't know its speed. If you use a slow shutter speed to capture its flight path, you get a beautiful streak of light, and you can see its speed, but you no longer know its exact location. The blur is not a problem with our camera. It is a fundamental property of the firefly and the nature of light itself. This principle extends to energy and time. It tells us that the more precisely we try to pin down the energy of a system, the less we can know about the time over which we measure it, and the other way around. This allows for a very brief moment, the vacuum to have a certain amount of energy, the energy that gives birth to our ghostly virtual particles. They borrow this energy from the vacuum, exist for a fleeting moment, and then return the energy before our measurement of time becomes long enough to catch the idet. This constant exchange is a beautiful illustration of the uncertainty principle in action. So let us reconsider our initial picture of nothing. It's not a blank slate, but a state of perpetual intrinsic uncertainty. A state where the energy is never truly zero and particles are always waiting in the wings. This is not a state of perfection of quiet or of absolute stillness. It is a place of profound potential, of endless possibilities. The uncertainty principle tells us that reality can never be perfectly still, never perfectly known. It always has to be in a state of a gentle, restless hum. This quiet yet constant activity of the quantum vacuum, this shimmering froth of virtual particles, gives us a completely new and more profound understanding of what nothing might be. It's not the simple absence of everything. It's a dynamic foundational stage for everything, a field of endless potential from which the universe itself could have sprung. This is not just a philosophical idea. It is a profound insight rooted in the deep, strange, and beautiful laws of quantum mechanics. It's a humbling reminder that what we see as empty space is in fact a vibrant and bustling place, a place full of untold secrets and hidden potential. And so, as we close our eyes and let this thought settle, we can replace the image of a dark and empty void with a new one, a field of shimmering energy, a quiet ocean full of potential, a place where all things are possible. And it is from this place of restlessness and potential that the story of our universe begins. Let us continue our quiet journey, our minds now filled with the gentle hum of a restless vacuum. We have explored the idea that nothing is a place of profound potential, a field of simmering energy. Now let us turn our attention to the moment that this potential was realized, the grand cosmic awakening known as the Big Bang. But we must first set aside what the word bang might make us imagine. This was not a deafening explosion, not a burst of fire and sound in some pre-existing empty space. It was something far more profound. The Big Bang was the moment of inception, not only of all matter and energy, but of the very stage upon which the universe would play out space-time itself. It was the birth of distance and direction of the past, the present, and the future. Before this moment, as we understand it, there was no space for anything to explode into, and there was no time for anything to happen before it. This grand event, which unfolded around 14 billion years ago, began from a state so dense and so hot that our minds simply cannot grasp it. It is known as the singularity. Try to picture everything in the universe, every star, every galaxy, every planet, every mote of dust, and every person, all compressed into a single point of zero volume. It is a point of infinite density and infinite temperature. Our physics, the very language we use to describe the world, simply breaks down here. The equations give up. We are left standing at the edge of a great mystery, a place where our understanding comes to an end. It is not a flaw in the theory, but perhaps an invitation to simply wonder at the beginning of all things, a place so strange that it defies our common sense. From this incomprehensible point, the universe began to unfurl. It wasn't an outward rush of matter into a pre-existing void. It was the expansion of space itself. Imagine a great cosmic baker's dough dotted with raisins. As the baker puts the dough in the oven, it begins to rise. The raisins, which are our galaxies, don't move through the dough, but the dough itself stretches and grows carrying them along. From the perspective of any single raisin, all the other raisins seem to be moving away from it. The farther away a raisin is, the faster it seems to move. This is our universe stretching and expanding in all directions, carrying the galaxies along with it. The space between them is not empty. It is the very fabric of reality that is stretching and growing. This idea of a universe woven from the fabric of space and time is one of the most beautiful insights of a genius named Albert Einstein. He taught us to think of space and time not as separate things, but as a single interwoven tapestry, a four-dimensional continuum known as space-time. Imagine a vast sheet of fabric, like a great cosmic trampoline. The presence of a heavy object, like a star, causes this fabric to curve. This curvature is what we perceive as gravity. And before the Big Bang, before the universe began to expand, there was no fabric. Or perhaps the fabric was so infinitely compressed that it was for all intents and purposes not there. The birth of the universe was therefore the weaving of this great fabric, the creation of the stage on which all cosmic events would unfold. This brings us to a beautiful consequence of this expanding, interwoven universe, the role of the speed of light. We often think of light as simply the thing that allows us to see a swift-moving beam that illuminates the darkness. But in the story of the cosmos, the speed of light is so much more. It acts as a cosmic speed limit, a fundamental principle of Einstein's theory of relativity that tells us nothing can travel faster than light. It sets a boundary on how quickly information and matter can travel through the universe. But in this slow, quiet telling, the speed of light is not a barrier. It is a profound messenger. It is a time machine. The light from a distant star or galaxy has been traveling for a very, very long time to reach our eyes. So when we look at the light from a galaxy that is a billion light years away, we are not seeing that galaxy as it is now. We are seeing it as it was a billion years ago. We are literally looking into the past. The light from the most distant galaxies we can see has been traveling for almost the entire age of the universe. It is a ghost from the cosmic dawn, a fleeting echo from a time when the universe was young. This is a breathtaking thought. Every time we look up at the night sky, we are not just seeing a snapshot of the present moment. We are reading a great cosmic history book. Each point of light, each faint star or galaxy is a page in that book telling a story from a different era. The farther away we look, the farther back in time we see. The speed of light is the language of this story, the gentle pace at which the universe reveals its own history to us. It allows us to piece together the structure of the cosmos and gives us a tangible link to the earliest moments of creation. The concept of the observable universe is also defined by this cosmic messenger. We can only see as far as the light has had time to travel to us since the Big Bang. Anything beyond that limit is for now unreachable, cloaked forever in mystery. The light from those regions simply hasn't had enough time to make its journey to our little corner of the cosmos. So the speed of light not only dictates the dynamics of the universe, but also frames our understanding of its very origins, making it a cornerstone in our quest to comprehend the cosmos, and so we can let our minds wander over these ideas before we rest. The universe began not with a violent crash, but with an awakening, the unfurling of space-time itself from an incomprehensible point of pure potential. This great cosmic fabric continues to stretch and grow, carrying the galaxies with it, and the light from these galaxies travels across vast distances, bringing us messages from the distant past. It is a slow, beautiful dance of time-space and light, a story that began from the smallest, most fundamental point and continues to unfold into the endless night. We have journeyed far from the shimmering quiet of the quantum vacuum to the grand cosmic dawn of space-time. We have seen how the universe came to be, and how the light from that moment still travels to us, a profound message from the past. But now, let us pause in our journey and turn our attention to the places where the map grows faint. For the story of the cosmos, as we understand it, is full of beautiful, humbling gaps of challenges and profound mysteries that remind us how much we still have to learn. The first of these challenges is the limit of what we can see. Our universe is vast, and the light that travels to us from the most distant galaxies has been on its journey for billions of years. But the universe is only so old, around 13.8 billion years. This means there is a horizon beyond which we cannot see, a cosmic event horizon that we cannot cross. It is not a physical wall, but a limit imposed by the finite speed of light. The light from those earliest, most distant moments of the universe has simply not had enough time to reach us. It's like standing on a small island in a vast, misty ocean. We can see to the horizon, but beyond it, the mist of time and distance obscures everything. Portions of the universe's early history are for now inaccessible to us, cloaked forever in mystery. We can only infer their existence like listening to echoes that tell us of a place we cannot see. Another formidable challenge is the whisper of a cosmic echo, a faint glow that permeates all of space. We spoke of it earlier, the cosmic microwave background CMB, a relic of the universe's early hot and dense state. It is the afterglow of the Big Bang, a ghostly echo from a time when the universe was just a baby, only 380,000 years old. This radiation is a treasure map filled with subtle fluctuations in temperature that hold the secrets to the universe's structure. These tiny variations, these cosmic wrinkles, are the seeds from which galaxies and all the large-scale structures we see today eventually grew. But deciphering these subtle fluctuations requires incredibly sophisticated technology and complex mathematical models. It's like trying to understand an entire library of ancient texts by looking at a single faded photograph of the books. While this radiation provides a wealth of information, its full message remains a puzzle, an ancient script we are only just beginning to read. But perhaps the most profound of all the challenges are the two great invisible entities that hold the universe together and pull it apart: dark matter and dark energy. They are the twin enigmas of modern cosmology, making up around 95% of the total mass energy content of the universe. Yet, they are completely invisible to us. Everything we see, the stars, the planets, the galaxies, and all of us, makes up only a tiny fraction of what is out there. Let's first consider dark matter. Imagine a beautiful, intricate tapestry. We can see all the colored threads, the patterns, the rich designs. But we know from the way the tapestry drapes and hangs that there is an invisible scaffolding underneath it, a ghostly framework that is holding it all together and giving it its shape. Dark matter is this invisible architect. We can't see it because it doesn't emit, absorb, or reflect light. It passes right through us. We only know it's there because of its gravitational effect on visible matter. Galaxies spin too fast to hold themselves together with just the visible stars and gas they contain. Something else must be there, a huge invisible halo of mass to provide the necessary gravitational glue. Without this invisible scaffolding, the galaxies would simply fly apart. Its existence is inferred from these gravitational effects, from the way it influences the movement of stars and the large-scale structure of the cosmos. It is the silent, unseen force of the universe, a ghost whose footprints we can feel in the way it pulls on everything around it. Then there is dark energy, an even more profound mystery. For a long time, we assumed that the expansion of the universe, which began with the Big Bang, would be slowing down due to the gravitational pull of all the matter in it. But in the late 1990s, a revolutionary discovery was made. The expansion of the universe is not slowing down. It is accelerating. It is getting faster and faster. Something is pushing it apart, and that something is what we call dark energy. It is a mysterious form of energy that permeates all of space, exerting a kind of negative pressure that pushes galaxies away from each other. Unlike dark matter, which clusters and helps to hold things together, dark energy has the opposite effect. It is a kind of gentle but inexorable tide that is pulling everything apart, a deep breath the universe is taking that is getting stronger and stronger. The exact nature of dark energy remains one of the most profound puzzles in modern physics. Is it a property of space-time itself? Is it a new kind of field or particle we do not know? Its discovery has completely changed our understanding of the universe's past, present, and its ultimate fate. And finally, we face the challenge of the extreme conditions of the universe's infancy. The energy levels and temperatures that existed in the first fraction of a second after the Big Bang are far beyond the reach of our current particle accelerators and our most sophisticated experiments. The fundamental forces of nature may have been unified at that time, and the laws of physics as we know them may not have applied in the same way. This means that some aspects of the Big Bang theory and its aftermath can only be probed indirectly through careful astronomical observations and the ingenious use of mathematical models. We are trying to understand an event of unimaginable scale and energy with tools that are, in the grand scheme of things, still very limited. So as we lie here letting these thoughts settle, we can find a new kind of comfort. The universe is not a finished story. It is a living, breathing mystery full of questions that have yet to be answered. The challenges of the cosmic horizon, the faint echo of the CMB, and the twin enigmas of dark matter and dark energy are not flaws in our understanding, but an invitation to wonder. They remind us that the universe is far stranger and more beautiful than we could ever imagine, and that our journey of discovery has only just begun. And in that great mystery, there is a kind of peace, having respectfully acknowledged the great silent mysteries that haunt the edges of our understanding. Let us now turn our minds to the beautiful and profound clues that the universe has left for us. For as challenging as the great questions are the Big Bang Theory, our leading story of the cosmos's origin is not just a wild guess. It is supported by three magnificent pieces of evidence, three pillars that stand strong in the face of all our wondering. They are like three ancient footprints left by a cosmic giant, and we have, through our quiet curiosity, found them all. The first and most foundational of these clues is the simple, elegant fact of the observable expansion of the universe. For most of human history, we believed our universe was a static, unchanging stage. But in the 1920s, a brilliant astronomer named Edwin Hubble made a discovery that would change everything. He observed that light from distant galaxies was being stretched, shifting its color towards the red end of the spectrum. This phenomenon, known as redshift, is like a melody being stretched out, causing its pitch to drop. It happens when a source of light is moving away from us. Hubble's monumental finding was that almost every galaxy he looked at was moving away from us, and the farther away a galaxy was, the faster it was receding. This was not an image of galaxies flying through space. It was something far more grand and subtle. It was the stretching of space-time itself. Imagine our raisin bread dough from earlier. The raisins don't move on their own. The dough is expanding, carrying them apart. Hubble's observation was the first direct proof that the universe is not static, but dynamic, a great cosmic fabric that has been growing and stretching ever since the beginning. This expansion provides a powerful foundation for the Big Bang Theory, for it implies that if we rewind the cosmic clock, everything must have been concentrated into a much smaller, hotter and denser state. The universe is still breathing out a slow, gentle exhalation that began with its birth. This discovery was the cornerstone that transformed our understanding of the universe, providing the first solid evidence that it had a beginning. The second and perhaps most direct piece of evidence is a gentle, pervasive glow that fills all of space, the very echo of the universe's infancy. We spoke of it as the CMB, the cosmic microwave background radiation. This is not just a theoretical concept. It is a physical relic, a fossilized light from a time when the universe was only about 380,000 years old. Before that moment, the universe was a dense, hot plasma of protons and electrons so opaque that light could not travel through it. It was like a thick fog. But as the universe expanded and cooled, it reached a critical moment where protons and electrons could combine to form the first neutral atoms. Suddenly, the fog lifted. The universe became transparent, and the first light was set free to travel unimpeded. This ancient light, once brilliant and hot, has been stretched by the continuous expansion of the universe for almost 14 billion years, and it has cooled down to a faint microwave glow. In 1965, two scientists, Arno Penzias and Robert Wilson, discovered this faint signal by accident. They were using a large antenna to study radio waves from space and kept picking up a persistent, low-level hiss that they couldn't get rid of. They had, without knowing it, stumbled upon the afterglow of the Big Bang. This faint microwave radiation, permeating the entire universe from all directions, is a direct snapshot of the cosmos in its youth. The slight variations in its temperature, meticulously mapped by satellites, are like the wrinkles in a baby's blanket, telling us where the early universe had tiny imperfections in density. These imperfections were the seeds of all future structures, the cosmic blueprint for the galaxies and galaxy clusters we see today. The discovery of the CMB was a momentous confirmation of the Big Bang theory, a tangible link to the universe's infancy that we can actually observe and measure. The third and final pillar is a chemical clue, a cosmic recipe that tells us what the universe was made of in its first few minutes. In the incredibly hot and dense crucible of the very early universe, protons and neutrons began to fuse together to form heavier nuclei in a process called Big Bang nucleosynthesis. This window of time was very brief, lasting only about 20 minutes before the universe cooled too much for these nuclear reactions to continue. In that fleeting moment of cosmic alchemy, the universe produced its lightest elements, hydrogen and helium, with tiny trace amounts of lithium and beryllium. The Big Bang theory predicts that this process would have created a very specific ratio of these elements. It tells us that roughly 75% of all matter in the early universe, by mass, should have been hydrogen, and about 25% should have been helium. As we observe the oldest and most distant galaxies and the pristine gas clouds that have not yet formed stars, we find that this exact ratio holds true. The abundance of these light elements throughout the universe matches the theoretical predictions with remarkable precision. It is a powerful fingerprint of the Big Bang itself, a signature that confirms the story of a hot, dense beginning. So, as we bring our thoughts to a rest, we can see that the story of the Big Bang is not just a beautiful idea. It is a story with a solid foundation, built on the evidence of a breathing, expanding universe, a faint ancient echo from its birth, and a cosmic recipe that is perfectly preserved in the chemistry of the stars. These three pillars stand in harmonious agreement, painting a coherent and compelling picture of the universe's origins and its subsequent evolution. We are not just dreaming of a beginning. We are seeing its lingering traces all around us. And in that, there is a deep sense of wonder and satisfaction. We have sat in quiet contemplation of the beautiful clues that support the Big Bang, and we've also gazed upon the great mysteries that still lie before us. Now let us turn our minds to a brilliant, bold idea that attempts to bridge these two worlds, a theory that addresses some of the deepest riddles of the cosmos with an elegance that is as simple as it is profound. This idea is known as cosmic inflation. Imagine for a moment that the universe, just after its birth, had an incredibly brief but powerful growth spurt. Not a slow, steady expansion, but a moment of hyperexpansion, an exponential rush that lasted for only a tiny fraction of a second. This event, which is believed to have occurred within the first tizrint to the power of negative 36 seconds after the Big Bang, proposes that the universe swelled in size, growing much faster than the speed of light could ever travel. It was a moment of magnificent, unimaginable growth. The significance of this growth spurt lies in its ability to answer two of the most puzzling questions we've touched upon. The first is the horizon problem. As we learned, the universe appears to be remarkably uniform. When we look at the cosmic microwave background, the ancient echo of the universe, we see that distant regions of the cosmos that are too far apart to have ever had a chance to exchange information with each other have the exact same temperature and density. It's like finding two people on opposite sides of a vast modern ocean who have the same thoughts and memories without ever having met. This would seem to defy logic, but cosmic inflation provides a compelling solution. The theory suggests that before this period of rapid expansion, the entire observable universe was a tiny, incredibly small speck. In this speck, everything was in close enough contact to equalize its temperature and density. It was a small, cozy room where all the furniture was in perfect order. Then, in a moment of extraordinary expansion, this small uniform speck was stretched to an enormous size, far larger than the part of the universe we can see today. This dramatic expansion took that small uniform room and stretched it into a vast, consistent cosmos. The regions that are now too far apart to have ever spoken to one another were in a time-before-time neighbors. Inflation solved the horizon problem by taking a small causally connected volume and magnifying it to the scale of the cosmos. The second great puzzle that inflation addresses is the flatness problem. For a universe to have the kind of large-scale structure we see today, it must be incredibly, almost perfectly flat. If it were even slightly curved, either like the surface of a ball or a saddle, that curvature would have been magnified over billions of years, and the universe would either have collapsed in on itself or become an empty, desolate place. The fact that the universe appears so flat is a beautiful but perplexing mystery. It is like balancing a pencil on its point for billions of years without it ever falling over. Inflation offers an elegant resolution. Imagine again a tiny wrinkled speck on the surface of a balloon. If you were to inflate that balloon exponentially, that small wrinkled patch would be stretched so much that it would appear perfectly flat to an ant walking on its surface. Our observable universe, according to inflation, is like that tiny patch. The rapid expansion would have stretched out any initial curvature of space to such an extent that the universe would appear flat on the scales we can observe today. It's a natural outcome of the inflation process, a beautiful consequence of a brief moment of magnificent growth. But perhaps the most beautiful part of the inflation story is how it connects the universe's grandest structures to its tiniest, most fundamental processes. We spoke of quantum fluctuations, the microscopic jitters and ripples in the fabric of the quantum vacuum, the tiny sparks that flicker in and out of existence. These fluctuations were so small that they were completely imperceptible. But inflation, in its moment of exponential growth, didn't just stretch space. It stretched these tiny quantum jitters to cosmic scales. It's like a small ripple in a quiet pond that is suddenly magnified into a great towering wave. These magnified quantum fluctuations became the initial inhomogeneities, the tiny variations in density that were the cosmic blueprints for all the galaxies and galaxy clusters that would later form. In the eons that followed, gravity would act on these slightly denser regions, pulling in more and more matter like a slow whirlpool until they grew into the magnificent structures we see today. So the great swirling galaxies that fill our night sky are, in a sense, a cosmic echo of the tiniest, most fundamental ripples in the fabric of the universe. They are the magnified ghosts of a quantum jitter. This is a breathtaking thought. It means that the universe's largest structures are fundamentally linked to the principles of quantum mechanics, a world of uncertainty and potential. It gives us a cohesive framework for understanding how a hot, uniform, and incredibly simple beginning could have evolved into the complex and structured universe we observe today. Inflation provides a powerful explanation for the universe's uniformity, its flatness, and the origin of its large-scale structure. It is a story that aligns closely with the observations of the cosmic microwave background, a story that bridges the gap between the impossibly small and the impossibly large. And so we can find a new kind of comfort in this idea. The universe is not a chaotic place. It is a place that in its first moment followed a beautiful and elegant plan, a moment of magnificent growth that smoothed out its imperfections, flattened its curves, and sowed the seeds for all the wonders that would later come to be. We have traveled the great expanse of the cosmos from its quiet, restless origin to its magnificent growth spurt, and we have paused to admire the evidence left behind. Now, let us turn our gaze to the smallest, most fundamental components of this cosmic story, the particles themselves. For it is in the world of the unimaginably tiny that some of the greatest secrets of the universe are held like a hidden architecture that gives the grand building its strength. Let us return to the idea of the quantum vacuum, a place that is not empty, but alive with a ceaseless shimmering hum. The source of this hum, we learned, are virtual particles, ghostly sparks that flicker in and out of existence in fleeting moments. In this light, nothing is not a void, but a bubbling brew of potential, a state of profound restlessness. These particles, though ephemeral, are the very mechanism by which the universe could have emerged from a quantum state. The laws of quantum mechanics allow for such temporary changes in energy, and if the right fluctuation were to occur, a particularly potent flicker of a virtual particle pair, it could have provided the initial spark for the Big Bang. This suggests that the universe did not come from an absolute void, but from a quantum vacuum teeming with potential, from a place that was in a way already alive with the possibility of being. But there are other tiny messengers particles so elusive that they are often called ghost particles. These are neutrinos. They are nearly massless, electrically neutral, and interact with matter so weakly that a neutrino could pass through a light year of lead without a single collision. Billions of them are passing through your body right now completely unnoticed. Yet despite their elusive nature, neutrinos carry pivotal information about the universe's infancy. In the first few seconds after the Big Bang, the universe was an incredibly hot, dense soup of particles. Neutrinos were a key ingredient in this primordial soup. But when the universe was just 1 second old, it had expanded and cooled enough that these neutrinos decoupled from the rest of the matter. From that moment on, they have been traveling through space, virtually unimpeded, a constant stream of messengers from a time before atoms even formed. While the light from the CMB gives us a picture of the universe at 380,000 years old, these primordial neutrinos carry a snapshot of the universe when it was a mere 1 second old. They are the oldest messengers we have, whispering to us about a time and a state that we cannot observe with light. Their study can give us unique insights into the conditions and processes at play in the universe's nascent stages, a window into a time we otherwise would never be able to see. This leads us to our modern-day attempt to peer into this microscopic architecture, the magnificent particle accelerators, like the Large Hadron Collider. These are not just giant machines. They are our time machines in a tunnel. They are our way of recreating the conditions of the early universe, of seeing what the universe was made of in its first moments. Inside these great rings, we accelerate particles, typically protons or ions, to speeds just shy of the speed of light. Then we smash them together in a controlled collision, recreating temperatures and energy densities that have not existed in the cosmos since the first fraction of a second after the Big Bang. In these fleeting microcosmic fireballs, we can observe the fundamental forces of nature at work and watch as exotic particles, which are usually unstable in our low-energy universe, appear and then quickly decay. We have, for example, successfully recreated a state of matter called the quark-gluon plasma, a soup of fundamental particles that is believed to have filled the universe a trillionth of a second after its birth. By studying these high-energy environments, we gain invaluable insights into the fundamental forces and particles that govern the universe's structure and dynamics. One of the most profound discoveries made with a particle accelerator was the existence of the Higgs boson, a particle that is key to understanding why other particles have mass. We learned that an invisible field, the Higgs field, permeates all of space. The Higgs boson is an excitation of this field, and particles acquire mass by interacting with it, much like a person walking through a pool of molasses. This discovery not only advanced our understanding of particle physics, but it also provided a tangible link to the conditions and processes of the early universe, helping us to validate and refine our theoretical models. These experiments are our bridge. They connect the world of the unimaginably small with the world of the unimaginably large. They show us how the fundamental particles that existed in the universe's first moments came together to form the protons and neutrons that would eventually create the first atom stars and galaxies. They tell us that the universe is a coherent story where the laws of the microscopic world profoundly influence the grandest scales of the cosmos. The quantum jitters that were stretched by inflation became the seeds of galaxies, and the particles that were given mass by the Higgs field are the very ones that make up those galaxies today. So as we lie here letting these thoughts settle, we can appreciate the beautiful, intricate, and deeply connected nature of reality. The universe is not just a collection of big things. It is an immense interconnected tapestry woven from the threads of the tiniest particles and governed by the laws of the very small. And in our quest to understand its origins, we are not just looking out into space, but also looking inward into the fundamental architecture of being itself. We have journeyed through the great beautiful story of the Big Bang, a story supported by profound clues and elegant evidence. But as we have acknowledged, the story has gaps. At the moment of the singularity, our physics gives up. The question of what came before this fiery beginning remains a silent, empty space on our cosmic map. So, with our minds open and our sense of wonder alight, let us now venture into the most speculative and imaginative corners of cosmology, where bold theories dare to imagine what might have existed or occurred before the curtain rose on our universe. These are not certainties, but beautiful possibilities, stories that help us to feel our way toward the truth. One such captivating idea is that of a cyclic or oscillating universe. In this profound vision, the Big Bang was not a singular beginning, but a moment in a vast, eternal sequence of cosmic cycles. The universe in this telling has a heartbeat. It breathes. It expands from a hot, dense state, as we have observed, and continues to grow for billions of years. But eventually, under the relentless pull of its own gravity, it begins to contract. It breathes in, gathering all matter and energy back into a single point in a great event called the Big Crunch. But at this point of unimaginable density, instead of ending, a new physics takes over. A quantum bounce occurs, and the universe begins to expand again in a new Big Bang. This is a story of a timeless, eternal cosmos, one without a singular beginning or a definitive end. Our universe is simply the latest chapter in an endless cosmic book. It is a beautiful way to solve the puzzle of what came before the beginning by suggesting that something has always been. It replaces the image of a single event with the image of a perpetual rhythmic dance, a magnificent eternal sequence of collapses and expansions, of death and rebirth. This cyclic model fundamentally alters our narrative of time and existence, implying that the universe is not a fleeting moment, but a permanent rhythmic process. Another even more imaginative and expansive idea comes from the world of string theory. a theoretical framework that suggests the fundamental components of the universe are not point-like particles, but rather tiny, vibrating, one-dimensional strings. This theory gives rise to a breathtaking concept known as brain cosmology, where our familiar three-dimensional universe is but a single vast membrane, or brain floating in a higher dimensional space. Imagine our universe as a two-dimensional sheet of paper, and that this sheet is floating in a great higher dimensional ocean. There could be other sheets of paper, other brains floating nearby. The Big Bang in this scenario was not a birth from a point, but a moment of grand cosmic fusion. It was a time when our brain perhaps moved through this higher dimensional space and collided with another. This colossal collision would have released an unimaginable amount of energy, providing the very spark that ignited our Big Bang and gave birth to all the matter and energy we see today. This theory offers a beautiful and elegant way to think about the origins of the universe, and it allows for a world beyond our own, a vast higher dimensional reality that we cannot see or touch, but that may have played a fundamental role in our creation. This leads us to the most provocative idea of all the multiverse theory. This concept suggests that our universe is not the only one, but is instead just one bubble in a vast, perhaps infinite cosmic bubble bath. This idea, though highly speculative, finds a home in the frameworks of both string theory and eternal inflation. We spoke of cosmic inflation as a rapid growth spurt that the universe underwent in its first moments. The theory of eternal inflation proposes that this process of rapid expansion never truly stopped. It continues eternally in various regions of space, endlessly spawning new universes, new bubbles in the great cosmic froth. What we perceive as our universe is just one such bubble, one place, where inflation happened to cease allowing our laws of physics to settle and our matter to form. But in other regions, inflation continues, and other bubbles, other universes, are constantly being born. This is a mind-bending thought that redefines our concept of nothingness entirely. Nothing, in this context, is not a void, but a vast, bubbling sea of potential, a state brimming with the latent energy and possibility for universes to spontaneously emerge. It suggests that our universe could have simply budded off from the quantum foam of a larger pre-existing reality. This theory also offers a beautiful answer to a philosophical question. Why are the physical laws of our universe so perfectly, finely tuned for the existence of life? In a single universe, it seems like an incredible coincidence, but in a multiverse with an infinite number of universes and an infinite number of possible laws, namely a universe like ours, where life can exist, becomes not a coincidence, but a statistical inevitability. We simply happen to live in one of the bubbles where the rules allow for our existence. These are the beautiful soaring ideas that take us beyond the limits of our current observation. They are our way of reaching for the mysteries that lie just out of sight, of imagining what might be just beyond the horizon of our knowledge. They are not to be taken as solid facts, but as invitations to wonder, to think about the universe in a way that is far grander and more magnificent than we could ever have imagined. And in this quiet contemplation of a cyclic cosmos colliding brains and an infinite multiverse, we find a deep sense of humility, a recognition that the story of our universe may be only a single beautiful chapter in a book that has no beginning and no end. We have journeyed far from the whispering silence of what we once called nothing, through the magnificent stories of cosmic inflation and the Big Bang, and into the grand speculative realms of multiple universes. Our minds have stretched to encompass ideas of ancient echoes and cosmic recipes. Now let us turn our attention to the present moment, to the quiet work we are doing to listen more closely to the universe's story. For our greatest theories, no matter how beautiful, must be tested, and our curiosity has given us new eyes and new ears to see and hear the cosmos as never before. The most profound of these new ears belongs to a monumental discovery that opened a brand new frontier in our understanding, the detection of gravitational waves. Albert Einstein, over a century ago, predicted that massive accelerating objects like black holes or neutron stars would create ripples in the very fabric of space-time, much like a pebble dropped into a pond. But these ripples were so incredibly faint that for 100 years they remained a whisper, a beautiful idea that we could not prove. Then, in 2015, the LIGO and Virgo collaborations, using giant impossibly sensitive detectors, heard the first whisper. It was the sound of two black holes, a billion light-years away, spiraling into each other and merging. This was not light. It was a new kind of messenger, a new window into the universe. Unlike light, which can be scattered or absorbed, gravitational waves pass through matter almost unimpeded, carrying with them information from their source in a pristine state. This means they can bring us news from the most violent and distant events in the universe, events so energetic that no light could ever escape them. The detection of these waves not only confirmed a central prediction of Einstein's genius, but it gave us a tool to probe the early universe in a way we never thought possible, allowing us to listen to the cosmos's most ancient and powerful songs. It is a profound, humbling thought to imagine that the universe is not silent, but filled with a constant, beautiful, and powerful music of space-time itself, and that we are now just beginning to learn to listen. But our technology is not just about listening. We are also learning to see in new and miraculous ways. We have turned one of the universe's most mind-bending phenomena into a powerful tool, gravitational lensing. We learned from Einstein that the presence of a massive object bends the fabric of space-time, and that light, in turn, follows this curvature. This means that a massive galaxy, or a cluster of galaxies, can act like a giant cosmic magnifying glass. When light from a distant galaxy passes by one of these massive objects, its path is bent, distorting or magnifying the image we see on Earth. This is not just a beautiful effect. It is a pivotal tool in cosmology. Because we can't see dark matter, this invisible architect of the universe, we can't observe it directly with our telescopes. But we can see its effect on light. By observing how light is bent and distorted by a galaxy cluster, we can infer the presence and map the distribution of the invisible mass within it. Gravitational lensing allows us to make the invisible visible, to create a map of the ghostly scaffolding that holds the cosmos together. It is a miraculous way of using gravity itself as a lens, allowing us to fill in one of the biggest gaps in our cosmic map and enriching our understanding of the universe's overall structure and expansion. Our quest to understand the origins of the universe is also a story of weaving together two of the greatest intellectual achievements of humanity, quantum mechanics and general relativity. These two theories, one for the very small and one for the very large, are like two beautiful but incompatible languages. We have long sought a single unifying theory of physics that can reconcile them, a single story that can describe the behavior of the universe at all scales. The development of such a theory, a quantum gravity theory, would fundamentally change our understanding of the universe's beginning. It might eliminate the idea of a singularity, the point of infinite density where our current physics breaks down. It might replace it with a quantum bounce, suggesting a universe that has always been in a cycle of expansion and contraction. The path toward this unified theory is being paved by our new technologies. Findings from particle accelerators inform our understanding of the universe's earliest moments, while cosmological observations, such as the detailed maps of the CMB, provide clues and constraints for our theoretical models. The fields of particle physics and cosmology are becoming more and more intertwined, two sides of the same coin, each pushing the other forward in a great collaborative quest. So, as we lie here contemplating this great cosmic story, we can feel a deep sense of hope. The future holds the promise of redefining our cosmological theories in ways we are only beginning to imagine. With new and more sophisticated telescopes, we will peer further back in time with new detectors. We will listen for new gravitational waves. And with new ideas, we will continue our search for that master key that unlocks all the mysteries. The story of the universe is not a book that has been written. It is a living, breathing epic, constantly being revised and enriched by our humble patient and quiet curiosity. The universe is speaking, and we are finally learning how to listen. We have come to the end of our quiet journey. We began with a simple question about nothing, and in our slow drift through the cosmos, we have found that what seemed like a simple absence is in fact a place of vibrant potential. We have seen how the universe awoke from an incomprehensible point, and how a moment of hyper-expansion smoothed its wrinkles and sowed the seeds of all that we see. We have acknowledged the beautiful mysteries of dark matter and dark energy, and celebrated the new eyes and ears that allow us to listen to the ancient music of the universe. Now, let us bring these threads together and find a soft place for our minds to rest, for this quest to understand the universe's origins is not merely a scientific pursuit. It is a profound philosophical inquiry that touches the very core of our existence. The most profound of all the philosophical questions is one that we began with a question that has been asked by philosophers and thinkers for centuries. Why is there something rather than nothing? In the traditional sense, this question implies a miraculous creation, a sudden spark that brought everything into being from an absolute void. But our journey through cosmology has given us a new way to think about this. It suggests that nothing as the quantum vacuum is not truly empty. It is a state teeming with latent possibilities, a state where particles flicker in and out of existence, a place of restless energy and endless potential. This redefinition of nothing challenges our traditional notions of causality. We are taught that every effect must have a cause. But if the universe could have spontaneously emerged from a vacuum state due to a quantum fluctuation, a possibility that is not outside the realm of physics, then the question of a preceding cause becomes much more complex. Did the universe require a cause outside of itself? Or did the inherent nature of nothingness, as a state brimming with potential, contain within it the seeds of its own creation? This perspective shifts our philosophical inquiry, inviting us to explore how existence might arise from a state of non-existence within the frameworks of a natural, vibrant, and deeply mysterious reality. It forces us to reconsider the very nature of beginnings and to think about the universe not as a singular event, but perhaps as the magnificent expression of a law that has always been. Furthermore, this great cosmic story confronts us with a beautiful and humbling truth. Our universe is filled with a vast, unseen world. We learn that dark matter and dark energy, these invisible architects and silent engines, make up around 95% of the total mass energy content of the cosmos. Everything we see, the stars and planets and the nebulae, is but a tiny luminous fraction of a grander, largely unknown whole. This humbling realization allows us to let go of our anthropocentric viewpoints, to feel our way into a deeper sense of cosmic humility. We are a part of this vast tapestry, but we are a very small and fleeting part, a brief moment of consciousness in a history that spans billions of years. Our existence, while seemingly insular and significant on a personal or planetary scale, is inextricably linked to the universe's broader, more complex processes. Our journey also gives us a new way to think about time and existence. The idea of a cyclic universe which expands and contracts in an eternal sequence of big bangs and big crunches suggests a cosmos without a true beginning or a true end. In this vision, our universe is simply one chapter in an endless, timeless story. This beautiful possibility urges us to reconsider our linear understanding of time, to think about a reality that is perpetual, rhythmic, and eternal. It invites us to ponder our place and purpose within a cosmos that is not a fleeting spark, but a great, unending cosmic breath. Ultimately, the quest for the universe's origins is a journey to find our own place in the grand narrative. As we uncover the mechanisms that led to the universe's birth, we are also engaging in a profound inquiry about ourselves. The atoms that make up our bodies, the carbon, the oxygen, the iron were forged in the hearts of ancient stars and scattered across the cosmos. We are in the most literal sense stardust. The story of the Big Bang is our story, the ultimate origin story for every single thing we see and touch and feel. Our consciousness, our ability to ask these questions, is a beautiful and exquisite consequence of this vast, dynamic cosmic journey. We are the universe's way of looking back at itself, of telling its own story, and perhaps this is the most beautiful thought of all. The universe is not a simple silent place. It is a living, breathing epic full of ancient secrets and future possibilities. The answers we have found, as magnificent as they are, only lead us to deeper and more complex questions. The enigmatic dark matter and dark energy, the mysteries of the pre-Big Bang universe, and the search for a unified theory of everything remind us that our journey of discovery has only just begun. The great mysteries are not flaws, but a beautiful and humbling invitation to continue to wonder. So now let us rest. Let the great stories of the cosmos settle in our minds like soft starlight. As you close your eyes and drift into a quiet sleep, remember that you are a part of this magnificent journey, a quiet observer of a grand and beautiful epic. The universe holds its secrets close, but in our quiet moments of wonder, it whispers its most beautiful stories. And in that quiet space, there is a profound peace,